Okay, yes. So the talk will be in English, so that's basically discomposed of like three parts. So there is some introduction about a bit of myself, a bit about like history of this problem and stuff like this. Then there will be an overview of the methods and algorithms for pathfinding for mobile robots, and then we will switch to multi-robot setting when we have not a single robot but multiple robots, and each one wants to safely reach its goal. And in this part, I will talk mainly about results of our group, which we got recently, and that's basically it. And in case you have any questions, I think it's better just to stop me and ask them whenever you want, because otherwise there's going to be like a long gap between the slide and stuff like this. So it's okay. And yeah, we have a video recording, I believe. So in case someone doesn't feel uncomfortable, she's been like taped. There is an option to sit out of the camera. Okay, yes, so brief introduction about myself. So I'm PhD in computer sciences, and I work for more than 10 years for research center of Russian Academy of Sciences, which is now called Federal Research Center Computer Science and Control. That's my primary affiliation. That's where I work. There is this Artificial Intelligence Research Institute established within this center. I also work for Faculty of Computer Sciences of National Research University Higher School of Economics, which is hosting this tutorial colloquium, whatever. And basically, I'm with Faculty of Computer Sciences since it was established, since 2014. And also the member of Russian Association of Artificial Intelligence. And so basically my research interests are all about this. I like pathfinding very much. It was the topic of my doctoral thesis, PhD thesis. In Russian, it's called a bit like differently. It's not doctoral, but something else. We're using in our lab this heuristic search approach to solve these pathfinding problems. It's like kind of a special subfield of artificial intelligence. If we give a wider scope, it's all about intelligent robotics, about artificial intelligence. And I also got recently involved in some research considering multi-robot systems and settings. So before we start, a few words about like robots, who they are, because it's like nowadays this term is widely used, and even professionals, they cannot agree on what actually robot is. So I'm here on this slide you see a few definitions, and these definitions, they are taken from professional literature, from vocabularies or papers or even standards. And I like the latter one. I don't know what robot is, but I'll distinguish him when I'll see him. And basically, we intuitively, think that everything which is on the left part of the slide is a robot, while the coffee machine is not. But it's actually really hard to, if we want to go this formal way, it's really hard to come up with a definition according to which coffee machine won't be a robot. And there is always a confusion when two people talk about robots. Actually, they may be talking about complete different things, and yeah, that's a problem. So maybe what we have to do here, we need to put some adjective before this robot, like I did it in this lecture. So we're not talking about robots in general, but we are talking about some special sort of a robot. So, and it actually works. It narrows down the scope and it gives you an idea about what you're talking about, like, I don't know, wheeled robot or like flying robot. You get an idea that it flies, or I don't know, like humanoid robot that it looks like a human, right? So in the title of this talk, we have these guys on the right, mobile robots, and basically the key feature of the mobile robot by definition is that they can move in their workspace from one point to the other, right? So they can move from A to B, and that's the core feature of, that's the essence of mobile robotics. And obviously we want to automate solving this problem. It's not always needed actually in practice, right? So in practice we have like lots of tasks when, like this picture on the left, when actually the remote operation works perfectly for economical reasons or for whatever reason. So when we have like one robot and it needs to do like single shot task, for example, this aerial robot, it has to fly to some point and take some picture. So typically we have an operator which fully manually controls this drone, right? So it doesn't navigate by itself. But in case we have, for example, multitude of robots, multiple robots, so we have, I don't know, like 100 drones which are involved in, you know, like in some rescue operation going on in, I don't know, you know, like they have to find some group of lost people in the forest, and we have like a lot of robots, and we actually may not afford having, you know, like 100 of people remotely controlling them. So that's the evident purpose why we need this autonomous navigation in practice in real life, or like working in hostile environments or doing some repetitive tasks when you have to, you know, like to monitor some territory in like 24/7 mode. So I mean, like it's like a practical need, and from academic point of view, it has always been a very interesting problem, you know, like by itself. So I mean, like I'm from academia, I just like this problem. I'm not actually that not going deeply into how it can be applied like outside the lab, but it's very like interesting and challenging, because we think, okay, I'm a human, I can get from A to B, right? So let's make a artificial thing and let this thing also navigate the world around, like our world. So that's on this slide. You have this. Maybe you've seen this guy. It's the robot called Shaky. It's one of the prominent robotics projects which was in the late 60s, early 70s. SRI is Stanford Research Institute. It's not exactly the same as Stanford University, but it's a kind of like special research unit. It was actually, I mean, like this project, this Shaky project was mainly sponsored by, as you can guess maybe, by Army, by some Army agencies, but it was academic projects, and actually you can go follow this link and you can see a lot of, you know, like technical reports. They're all open and it's really cool. I advise you to go there to like investigate what was like state of the art at that time. And surprisingly, all the problems that were considered within these projects are pretty the same as we're like doing now, right? And there were a lot of very nice work. A lot of nice work has been done in developing those, you know, like intelligent methods and algorithms. For example, here I've put two like most prominent papers on which were released in connection with this project. So the STRIP system, which was for planning, for behavior planning, and another paper, influential one, was about like A-star algorithm, which was also used by for for finding a path by this robot. And so you can see that there is Nielsen as one of the co-authors of this paper. That's the famous guy who wrote this thick book, handbook on artificial intelligence, which is, I believe, it has now like fourth edition or so. It's recommended by most by a wide wide spectrum of universities as a handbook on introduction to AI course. So he was involved in this project. He was doing this stuff.
Sorry, and you said about this photo. So the gentleman in the photo, he is not a robot, right?
There are two gentlemen. Yeah, so which one are you talking about?
So the human one is really human.
Yeah. It's not Nelson, it's the one who wrote the proposal. Actually, there is I've seen the proposal to start this project, and they avoid using this term robot, because robot was really, like science fiction at that time. So, and they explain, in case we put robot in our proposal, the army guys just won't give us money. So they called it some sort of, like automatatron or some sort like this. So the project was called like this. Yeah, and the robot itself, it looks. There was no personal computers at that time. like IBM PC, so there were no digital cameras, but still it has like an analog camera on top. It has some computers, I believe DEC computers or whatever they used at this time. So it has wheels, caster wheel. So all the architecture, and it's basically, if you look at the modern robots used, like in the labs, they look pretty much like this. And I think it's very cool that it was, almost 50 years ago, or more than 50 years ago, and they have it. And but the reason they call it shaky, one of the participants of the project says that sometimes it just started, like shaking. Due to some disturbances in the control software, and they didn't know how to call it. And someone will say, let's call it shaky, and that's it. And yeah, and as for USSR, there is I couldn't find, although I even asked my peers from various institutions while I was preparing for this talk, I couldn't find the project which was like shaky, at Stanford Research. So an open project and like mobile robot, because robotics, it was like a huge the robotics was really evolved in USSR actually at this time, but it was mainly concentrated. People were mainly concentrated on on space robotics, on teleoperated robotics and stuff like this. But still, there were these are the photos from, for example, Institute of Applied Mathematics. So it's like 75, these hexapods. They were moving, and that's the picture from Leningrad State University, which is also like a mobile robots with with some sensors on it. So that definitely people were doing research in robotics in USSR, and actually the influence of Soviet, Russian scientists, it is evident, and we will find a few evidences of these further on. And even even at those times, they suggested what they suggested during Shaky, within the Shaky project, was this deliberative approach to navigation. So which means that we try to analyze the sensory information, the sensory input, and we want to not to throw it away, but we actually want to store it, to use it, to memorize it, and compose a coherent models of the environment, maps, and we want to further on use these maps to find a path. And here is the the four main subtasks of this navigation. I will talk about them further on a bit, but before I wanted to say that, I'll just spend 3 minutes, that actually when we're talking about navigation, about robot navigation, about going from A to B, there is an alternative approach called reactive approach, when you do not actually want to exploit the incoming data that much. You don't want to build coherent models of the environment. You just act in this stimulus reaction fashion. So you get some input, get some output, and forget about everything else. So that's so basically there is a whole bunch of algorithms. They're called bug algorithms, like bug, which is like a biological thing. So they just exploit like simple rules, and they behave very simply. So they just go in straightly from start to goal, and in case they encounter some obstacle, they do this, like wall following until some stop criteria is met, and when this criteria is met, they continue moving to goal. This results in weird-looking paths on the right, which you can see on the right, but it works actually, and you do not need to remember the map to build the map. You're just acting. You're just acting, and typically when we're talking about this reactive approach, about this bug navigation, so there is Vladimir Lumelsky, who wrote this paper and suggested this approach within the context of mobile robotics, and he worked also in USSR first in Institute of Control Sciences, then moved to United States, and this paper was written while he was already in the USA, but still again it's a Russian guy. Yeah, and there are a whole sort of this, like modification of this bug algorithm. So there is a whole family of those algorithms. So that's the picture which I've taken from this recent comparative study, which is available at Archive now, and so people are still doing this sort of thing. If we look through this, I can, for example, again name this publication. The co-author is Evgeny Magid, who now works in Kazan Federal University. So also he's a kind of like Russian-Israeli scientist. Now he's with Kazan Federal University. So again, it was just like that was to point out that this deliberative approach is not the only thing that we can do. We can also act in this like reactive fashion, but mainly robotic scientists, they are more interested in this deliberative approach, right? So when we need to create map first, then we need to find a path on this map, and then we need to make our robot actually follow this path. So this green arrow means that in this talk we will mainly cover actually this path planning problem. So we will assume that two top subtasks are accomplished. So we have a map, we have constructed it, and we also won't cover in details these path following problems. But again, to give you the whole picture, of course, I need to just to show you some examples at least. So as for localization and mapping, those two tiles of this navigation puzzle, so localization basically means that I have my sensory input, I have the map, and I need to estimate where I'm on this map, right? So I do not have location, I have to calculate it, I have to compute it. And mapping is a kind of like opposite problem. It has robot again has the sensory input, but it doesn't have a map, and he has to construct this map knowing its position and sensory input. Typically in robotics, we combine those problems into what is called simultaneous localization and mapping. So these four letters, SLAM, if you ask, like some guy from robotics, well, what is he doing? Chances are that he will go, I'm doing SLAM, right? So it's a very big subproblem there. The reason why those two problems are combined is that in many cases, even in practical cases, that's what's going on in real world. For example, imagine like some drone which has to perform some rescue operation inside the building. So when it enters the building, the GPS signal is lost, so it doesn't know where it is, so it doesn't have its location. So it has to localize itself, and it doesn't know the map of the building, right? So it has to map it, and that's why those two problems often come together, and that's why we're solving those problems all together as well. And for example, and solving this problem, it mainly comes down to what sensory input you have, what sensors are installed on the robot. For example, in 90s, it was very popular to do this LiDAR-based navigation when you have a laser rangefinder, typically like a scanning laser rangefinder, which can estimate the distance to the walls, to some objects, and that's what's going on when you're doing this SLAM with laser rangefinder, also called LiDAR on this slide. So here you can see the guy which is carrying this unit, but you can easily imagine that there is like a robot which actually drives in this indoor environment and maps it. So you see this map on the right, in the top right corner. You see this red is trajectory, so the trajectory is depicted in red. Gray is like the unknown environment. White or transparent is the free space, and those like walls which are marked in black, these are the obstacles. In case, for example, we have a drone, it's not that easy to install LiDAR on drone, because these sensors, they're not that very efficient in terms of power consumption. So they consume a lot of power. And in case we are talking about flying robots, drones, small drones which are flying inside the building, they're limited on their power resources. So typically indoor vision-based indoor SLAM for aerial robots is done with vision-based approaches. So when we have a camera, for example, in this scenario, it's the video from our group, it's in our lab. So there is this drone which flies inside our building, and you see that grayscale image. It's with this green squares. It's the video. And those green dots, these are the features of the images. So it automatically extracts features and tries to map it. So basically, those green dots on the video, they became those red and black dots on the map. So you can see the map on the right, the 3D map on top, and 2D projection on the bottom. That's how it is worked. So of course, you can note that this map is really a mess, right? So there are a lot of features that are actually shouldn't be there, and so it's actually not that easy to. So it's not that like nice map with like the corridors like you've seen with the LiDAR, but that's what it is. It's a very challenging problem. I do not know why it stopped, but there is but whatever. So and you can basically do something with this. So you can, for example, remove the outliers, upsample to get the nicer maps, like we've done with my PhD student. So you can do some post-processing and get nicer maps, which are more suitable for path planning. But the problem with this feature-based approach to simultaneous location is mapping is that obviously you do not have any metric information. So when you create the map, you do not know the scale of this map. So you know, for example, that this is the left wall, this is the right wall, but what's the distance between them in in meters, in some absolute values? You just do not know. It's getting very popular to overcome this difficulty with introducing some convolutional neural networks into the loop. So when we just get those meters from from the video flow, so we train the convolutional neural network, and then we just use it. So it's the same video, but here you can see how the depth reconstruction is done. So when the flight will start, I think, yeah. So it's the same video, but another processing thing. So here we do not have any trajectory thing. So we're not seeing the trajectory. We're not constructing the map. That's just for visualization purposes. That actually we can estimate the depth of the scene from a single image, and this processing is done actually not on board of the drone, but the data is transmitted to the laptop and is processed on the laptop. But what we're doing now in the lab is that we're trying to create, efficient architectures and implement efficient architectures to make this work on board, right? So we've bought some small NVIDIA computers and stuff like this. Any questions about this SLAM thing? Because we won't return to this. No, okay. So again, in this, I'm remembering that in this talk I will talk mainly about path planning, and I'm just giving the brief introduction, so you get idea of where you get the map from, right? So this SLAM thing is needed to provide you the map. So we have a map, and actually before we were diving into path planning, let's talk what's going on after we build the path on this map. So we have the map, we build a path. Imagine that we did it. So we need to follow it, and basically this is done. I'm not that that professional in this field. It's again the video from our lab. So we have this wheeled robot. It's it's the robot from 21st century, but look at it. It looks pretty much like shaky from from 70s, right? So it's pretty the same. So here you have this map on top. It has already been constructed. Here you have this red trajectory. It's the trajectory that has been planned, and then robot has just to follow this trajectory. And if you look at it, it's not that clear from the screen, but you see that there are some deviations. So while it's following the trajectory, obviously it cannot follow it precisely, right? So it just it's accumulating errors and stuff like this. And to cope with this, there is a whole bunch of methods to do. The keywords, again, I'm saying I'm not that professional in this part, but I know that this mainly is done with the help of the control theory. So all these model predictive control, flat system, closed loop controls, regulators, that's what it is. So they try to compensate these disturbances and make robot actually follow this path after it has been planned. So okay, so now I think that at least have some general picture about like what's going on, and we can actually look at this path planning thing. So, and again, if you have like any questions about what I've said, I think it's better to ask them now. No, okay. So that's the problem statement of the most simple pathfinding problem. But we need, it's used, you know, like as a test bed for the algorithm, because if we talk about, you know, like some complicated problems, they basically comes up that to the thing that we solve this basic version of this problem, and then we just tweak the algorithm to, you know, like for our setting. So we are working in 2 dimensions, right? So we have and the environment is static and fully observable, so we know everything about the environment. And basically this workspace is just like a bounded rectangle compound of the free space and the obstacles. So there are only obstacles and the free space where a robot can move. And our robot is like an open disk translating on a plane, so it can only translate, again, with constant speed. So, you know, like acceleration effects are neglected, so it just starts moving with constant speed. This is somewhat, you know, like unrealistic assumptions, but we need them, you know, like to start with something, then we can relax them. And actually there are robots that are like naturally fit these assumptions. For example, you know, like this drone. Obviously it doesn't look perfectly like an open disk, but we can like draw, you know, like a disk and say that, yeah, that's the drone, and it can go in any direction it wants. So it can strafe, it can go forward, backwards. So there is like no problem in translating in our arbitrary direction. And yeah, that's basically it. So although this problem statement is some sort of, you know, like a vanilla problem, it's not that, you know, like absolute mathematical abstraction. So, and so the state of the robot in this case is simply the coordinates on this plane, and path is a sequence of non-collision states. Those non-collision, we assume that we have some, I will talk it on the next slide, but we assume that we're having this collision function. We give this function the state, and it just returns true or false, whether this state is in collision or not. Yeah, that's the thing. So we we feed this function with some coordinates from our free space, and it says whether we have the collision or no. It depicted here on the right. So you see that these red circles, it means that these robot positions, these robot states are in collision with the obstacles, and other guys are not. In case we actually know all the obstacles explicitly, for example, they are polygons and all the vertices are given, we can do what is called in math Minkowski sum. Basically, we can inflate these obstacles, and then our robot just becomes a point in what is called configuration space. And the same thing about moves. We assume that we have some function which says us which move is feasible. And in our case, when our moves are just when robot is only translating, so there is, you know, like straight line moves. So basically, it is called often line of sight. So what we're doing, we're looking at this line of sight function. Yeah, and the collision function is basically estimating estimated whether the distance between the center of the robot and to the nearest point on the obstacle is less than its radius. That's basically it. And in general case, you can look at this paper. There is like a lot of like methods for collision detection between various geometric models, like which are described by like various forms. So this, in our case, we assume that this is given. We just ask, is it in collision or no? And this collision detector says us. What else do we need? We need some cost functions. So we will talk mainly about minimizing distance. So the shorter path, the better. But we can also, like look, for example, clearance of the obstacles. So we do not want our robot to move close to the obstacles because it's not safe, for example. So it can also be the objective and many other, like more functions. We can also look at those functions is not that we're trying to minimize them or like maximize, so optimize them, but we can look at them as hard constraints. For example, we're looking on all the paths that are located not closer than, like some predefined threshold to the obstacles. So these cost functions, they can be hard constraints. For example, like in this publication by me and my students. Or we can look at the multi-objective cost functions when we're looking, like for some Pareto optimal solutions and stuff like this. So that's also what people are doing. Here we will assume that we have only one function. It's the distance for the sake of simplicity. And basically, one of the most prominent approach is to turn this problem into this graph search problem, right? So what we do, we say that our vertices of the graph are states. In our case, these are just points on the plane. Moves correspond to edges. In our case, moves are really, like the straight line segments. Although they can be of weird forms, some Bezier curves or stuff like this, whatever we want. Weights are the distance between the points, as we said, because we want to minimize it. And yeah, we need to find a path. So basically what we need to discretize our environment, our continuous environment, and say we have a graph, and then we need to find a path on this graph. So what are the widely used graph models for this thing? So visibility graph is a very is the model which is known from computer vision, mainly from computational geometry, but it can be used in robotics. So that's one of the early papers which use this approach from 1979. And the thing is that in case you want some more, more modern thing, I really like this PhD dissertation by Wooden, made in Georgia Institute of Technology. He was a part of this DARPA project, and they used these visibility graphs for robot navigation. But let's talk a bit about this publication, which is like a really cited publication. If you are writing a paper and mentioning these visibility graphs in context of mobile robotics, you obviously would cite this one. If you go inside it, it has, I believe, like something like 8 links inside it, and one of the links, number 5 here, you see it's the link to Ignatiev, Kolakov, and Pokrovsky. So, and if you look at the bibliographical data, you will see this GRS and some weird number. So does anybody have an idea what it is? So there is this paper about pathfinding, which it's related to visibility graph because there's some sort of like saying that we will do this thing, and it was written in those late 70s, and it has this citation Ignatiev, Kolakov, and Pokrovsky, and which doesn't have like a journal name or stuff like this, but has something like GPRS report number 59, something like this. Any ideas?
Published by ATI.
Absolutely. So there was this, during the Cold War, it was this agency in the United States called this GPRS, something like Public Research Services, Joint Public Research Services, or something like that. It was funded by CAI, and so basically what was the task? The task was to take some publicly available books from Soviet Union or so-called, like Eastern Bloc countries, and to translate them and to put them in English. So basically, there is a book from 1972. It's the cover of this book is on the right, which was also about robots in Soviet Union. And this guy cited, and basically they just say in this paper that we're kind of following this approach. Again, I mean, like, just think about it, that we all, think that there was, no robotics in USSR or something. Yeah, here it is. So what other models? We have these Voronoi diagrams, which are very common, which are very popular when we are talking about this maximum clearance path. So in case of visibility graph, you actually get the true shortest path on the plane if you use it. If you use Voronoi diagrams, you can get the maximum clearance path, so you get the safest path. The problem is that originally the Voronoi diagram concept was for point obstacles. So in case the obstacle is a point, then we can define what Voronoi diagram is. And it's not that trivial to construct Voronoi diagrams in case we have these complex shaped obstacles, but still people are doing it. And again, I cannot I cannot mention that one of the pretty well cited papers which elaborates on Voronoi diagrams in robotics, in path planning, not robotics, but still path planning. One of the authors is Gavrilova. While I was doing my PhD thesis, I wrote her and asked to send me the copy of this paper because I was not with Higher School of Economics at that time. I didn't have access to all the papers, and she sent me. And yes, she worked in Canada somewhere, but yeah, she is also like former our citizen. What other graph models we have? We have these probabilistic road maps and rapidly exploring random trees. These are like very popular in robotics because like previous models I was talking like Voronoi diagrams and visibility graphs, they're more on the theoretical side of the problem. They assume that you have the perfect knowledge of what your obstacles are. So you are, so you have the vertices of the polygons that are the obstacles. But in case we only have this collision function, this collision detection function for moves and for states, we cannot assume this, and these models, they are suited for this sort of the problem. So basically we just randomly, semi-randomly actually, we probe the workspace, so we just put the dot somewhere and invoke our collision detector and ask it, is this state in collision or not? If it is not, we just put the vertex in our graph, and the same we do for the edges connecting different vertices, and it's driven by why it is semi-randomly, because there is a random choice, right? So if we invoke this algorithm twice or like more times, we will get different pictures, but they are controlled by some deterministic input parameters. So you you give some parameters, and then it based on these parameters, it it makes graphs like this or trees like this. The difference between probabilistic roadmap and RRT is basically that RRT is constructed while you are doing the search. So it is you are interleaving the graph construction and the search. That's why it is a tree. It is rooted in your start location, and it grows, and you search it. And this probabilistic roadmap, it's kind of like pre-processing phase. So you just cover your workspace with this graph, and then you later on you use it. And finally, what I will talk more about is those grids. So basically, you just tessellate your workspace with this square grid, and in the center of each grid cell, you invoke this collision detection function. And if it says that this state is not in collision, you mark the cell as unblocked. If it says that when your robot stands here, you are in collision, you mark it as blocked, so you have this model on the right. So the graph vertices are the centers of the grid elements, and the connectivity is basically 2 power k, whatever you want. So in case you want to allow only cardinal moves, you say that you have 4 neighbors, like 4 connected grids. If k is 3, it means that you have 8 neighbors, like you're allowing diagonal moves as well, and like you can go further, k4, 5, and stuff like this. You can also you can also use not square grids like on this picture, but for example, triangular grids or stuff like this, but square are the most popular. Okay, so we have any questions so far about those models? No questions. Okay. So how can we search the graph? So there is some. So we have this, obviously, when we have the graph, basically we can say, oh, okay, we know Dijkstra, we can go with Dijkstra, that's the paper, and all the volumes of this Numerische Mathematik journal in which this Dijkstra paper was published, they are available now in the Springer link, so you can actually go and look about this paper. It's like a three-page paper, I believe. And A*, I've given this citation in my talk already. So it was developed during this shaky project. Basically, it's like Dijkstra plus heuristic function for guiding the search. So algorithmically, they are very, very close to each other. We will see it on the next slide. But funny thing is that A* paper does not cite Dijkstra paper, although there is, like a almost 10-year gap between them. So I do not know how it happened, but yeah, it was actually one of the questions which were discussed. Last year I was at this symposium on combinatorial search, and it kind of celebrated the 50 years of A*, and there was a couple of cool talks from the pioneers of this A* think about how it was invented and stuff like this. And that's I've learned this fact from this guy on the left, Robert Holte. And I looked at this paper, and I also was surprised that yes, A* paper does not cite Dijkstra, although the difference between Dijkstra and A* is this like tiny piece of like code. So Dijkstra use like G values, and A* use G values plus heuristic estimates. So they're very close. Yeah, but that's the thing. So here, so you have this illustrations of how Dijkstra and A-star with heuristics work on grids. Obviously, heuristic functions, they contribute to faster searches. This green field, no, not green, but this gray is the vertices of the graph. These grid elements that were considered by the algorithm during the search. So you see that the search space of the resultant search space of Dijkstra is much more. I mean, like it consists of much more nodes than A-star. We can also use this weighting heuristic thing. So we just multiply our heuristic with some constant factor, and we get the solutions faster, but they are weird looking. And there is a very good old school book about actually what the properties of heuristic, what heuristics can we use, what we cannot, what are the theoretical properties of, for example, doing this. Highly recommended. There are numerous modifications of this A-star. I mean, like it's very hard to choose something to actually name. So this is just like the random thing basically, because there are really like a lot of modifications. So basically, we take A-star and we modified it in some ways. And like one of the most prominent modifications is called jump point search. It basically gives you one order of magnitude speed up while not compromising the optimality of your solution, because it is known that if you search with A-star and you use admissible heuristic, you get the optimal solution of your graph search problem. And you, in case you wish not to compromise the optimality of the solution, you can use this jump point thing and get the one order of magnitude speed up. The surprising fact that it was only invented, like in 2011, right? So a lot of people were looking at A-star on grids for for 50 years, but these guys came up with this enhancement only in 2011, and it's really cool. So basically, you can do the same if you want. Another prominent modification is so-called any-angle pathfinding. So A-star paths, they look kind of, like on this grid, they look unrealistic. They contain, weird turns because of this. In case this is 8 connected grid, so only cardinal and diagonal moves are allowed. And basically, we want something like this. And Alex Nash, which is not that Nash who did this, thing in before, but he introduced this theta star algorithm, which comes up with paths like you see on the right. And these guys, what they did is that they they invent some other algorithm which is optimal any-angle pathfinding on a grid, because this theta star is a kind of greedy approach, and it doesn't guarantee optimality, which is theoretically nice. And again, only 3 years ago, someone came up with an idea how you can actually construct an algorithm which will guarantee the optimality in this any-angle case. So, yeah. And by the way, the name of this algorithm is Anya. And I talked to this guy, Daniel Harabor, about it. He is originally from Romania, now working in Australia, I believe. And I said, cool, Anya is a Russian name. I like that you named the algorithm like this. And he was like, yeah, I know that that's the Russian name, because I'm from Romania and I have a neighbor or a peer, a colleague, and his daughter name is Anya. That's why when we came up with this algorithm, yeah, it was a kind of obvious choice. So it's like any angle, it fits nicely. So yeah, I liked it. modifications which is widely used in robotics is called D-star light. So basically, this was introduced by Maxim Likhachov, which is coincidentally another guy from Russia. He did this while he was in America already, in the United States. I do not know why, but still, I mean, like, people just go in a way and make their write papers there, but yeah, it's true. So this D-star light by Maxim Likhachov, it is based on this lifelong planning A, again by one of the co-authors is Maxim Likhachov. So basically that's the more realistic problem statement when we lift assumptions of that the environment is static. So this lifelong A, it is the questions which is under consideration is, okay, you have the environment, you've planned a path, and then something has changed. What will you do? Well, the naive solution is that you just replan from scratch, just re-invoke the algorithm. They came up with a strategy not to do this, but like somehow to smart analyze what changes, how the changes affect what steps you actually need to redo. That was the lifelong planning A, and when they interleaved with execution, it became the D-star light. And funny thing is that this D-star light, it was, I believe this paper was, I'm not seeing it, but it was in 21st century already. But this algorithm, it's exactly not exactly, but it uses as they said even in their paper, it implements the same navigation strategy as D-star. So it's the algorithm which was, like a decade ago, and they just kind of, like re-implemented, with using this LPA framework. But this is the one which is mostly used in this case. So you can see the application of this D-star light, and you can see that there is a big difference with this reactive approach that I've shown before, because it doesn't go, like the full, it doesn't follow the obstacle until the end of time. It continuously maps the environment and it reuses it in its strategy. So it treats the problem as the graph search problem, only the traversability of some edges change. That's basically what LPI star does. A lot of people ask me when I'm talking about this robotic, and okay, what about like machine learning? We know that machine learning is really like popular nowadays. So there are some machine learning is really good, like in manipulator control, when you have to grasp objects, right? When you have to learn how to grasp a bottle or stuff like this. This is typically preferred not as pathfinding, but as motion planning. But if we try to, there is a paper from 2017 from the group of Sergey Levine, try to guess, which try to use these neural networks and machine learning to this problem, but actually they come up with kind of good results for machine learning community, but not that, like good from robotics perspective. I mean that, like D-star light can do the same thing much faster and with much higher quality. So it's not that actually easy to, so it's not that easy task like, like some classification or stuff like this. What we're doing now with my student from Higher School of Economics, we're actually trying to do funny thing. We're looking at this pathfinding as an image generation problem, right? So we we just try to generate images that resemble the path. So here you can see on top, you can see the input. That's the image where there is the start pixel and the goal pixel. And here is the ground truth. That's the path that was found by A star. And that's the path generated by this neural network. So as you see, sometimes it actually does pretty well. But again, it's machine learning. It's very, very tricky one. So yeah, it's not that easy. Okay, so that was basically the overview part of the talk, and I have about 5 more slides about actually what I'm involved in now. It's about multi-robot path planning, but before we proceed to this, maybe any questions about previous chapter? Yeah.
I have a question. So does topological evolution or path planning appears here? So there is some activity around topological methods applied to, well, at least motion planning. I don't know about path planning.
There is I believe it's rooted in topological SLAM. So there is, when I was talking about the SLAM, I was talking that what we're doing in our lab, we want to get metric maps when you have the distances, but actually a lot of people, they're saying, okay, we do not want the distances, but we want some topology, right? We want some connectivity, that this is to this door is to the left of this hall and stuff like this. I believe that it's mainly on the SLAM part of the framework. So when you come up with this topological map, which is like a kind of graph, then you just run the algorithm as they are. I think so, but maybe maybe you can something to add to this thing. Any other questions about? Okay, so this multi-robot path planning, so it's getting very popular nowadays. And again, so for example, that's the video from automated warehouses of Amazon. They have these orange robots. What they do, they just move around the warehouse and they pick up these piles and they help people to sort goods and pack them. And basically, they help Amazon to earn more money. So that's the scenario we are looking on in our lab. So basically it means that you have some centralized multi-robot path planning. So you have some controller which knows everything about where each robot is, where it has to go, and stuff like this. So it's not the reactive approach. Here is the problem statement. Again, I won't go deeply inside it. It's just like the picture that we have a bunch of starts and bunch of goals. Each robot has to safely navigate from start to go without not colliding into each other. And again, even if you discretize this problem and say that, okay, the workspace is discretized to a graph, there is a publication saying that it is NP hard to get optimal solution minimizing these objective functions. So basically, in this case, what sort of objective functions do we have? Obviously, for example, we can try to minimize the flow time. So we know the time of how long it takes for each robot. We plan the trajectory for each robot, and there is a time which it spends following this trajectory. So we can just sum them up, and we get what we have, like the flow time. The make span is the maximum over the individual times. So it's basically the time when the last robot will accomplish the mission, right? Or you can forget about time and you can say we're interested only in the length of trajectories, but no matter which objective function you choose, if you want to come up with optimal solutions, they prove that it's NP hard, so you're in problem. And what community, how community cope with these things? So basically, the conventional assumptions, they are very restrictive in this case. For example, time is typically discretized into time steps. So we have 1, 2, 3, 4, 5, and stuff like this. And the duration of every action is one time step. And actions are you can move or you can wait. Right? So you can move or you can wait. And only two questions? Oh, no, that's, yeah. And typically only two sorts of collisions are considered is head-on collisions when two robots try to use the same graph edge in the opposite direction, so they like colliding head-on, or there is a mid-collision when one robot is waiting, occupying some graph vertex, and another tries to move to it. And all these assumptions, they naturally translate to this sort of grids. So we have a grid which, when we allow only cardinal moves, because if we want to allow some other sort of moves, we cannot satisfy these assumptions that number 3 assumption, that the duration of every action is one time step. Because obviously if you go like diagonal, you have square root 2, so you're in problem. But that's the approaches that are tailored to solve this multi-agent pathfinding on grids. So basically what the simplest thing you can do, you can say, okay, I will just apply A star, but my state space will be the Cartesian products of the individual search spaces, which is like really, it doesn't work for more than like 3 robots in practice, right? You just cannot do the Cartesian products of the workspace and think that it works for sure. There are some decoupling techniques like conflict-based search. This is a very popular algorithm, CBS, very, very popular, M-star, or you can decouple problem in some way. For example, in our research, we're using this prioritized planning. So when you basically assign priorities to robot, and then you plan sequentially one by one, and previously planned robots, they are becoming dynamic obstacles. So you cannot choose their trajectory anymore. You just have to avoid collisions with them, right? And some other approaches. So that's what we're doing in the lab. So here are some references about, like, say, like traditional approaches. So that's what we investigated in this 2016 paper. We wanted to go beyond the basic setting, and we want those any-angle paths to be present on a grid, which makes that the conflict zone now is not just an edge of the graph or some particular vertex. There is, like some blob there in orange, and you have to do something about it. And actually, the conflict can occur at any moment of continuous timeline. So the timeline is continuous now. So not like discrete time steps, but yeah, so we're in problem. What we suggested is, doing this prioritized planning. As I've said, assign priorities to each robot and then plan one by one. And we modified the individual planner, AACIP, to handle these any angle moves and conflict and combine it all together. And our algorithm, AACIP-M, it tries to minimize objective function, but it does not guarantee optimal solutions. So it's not an optimal algorithm. Moreover, it's not complete in general because its prioritized planning is not complete in general, so we cannot do nothing about it. If you choose the wrong priorities, you can be in trouble. But those guys say that in case you have special sort of the workspace and start and go locations called well-formed infrastructure, this prioritized planning is complete, and basically this well-formed infrastructure means that each robot standing on its start or go location is not blocking other robots from accomplishing accomplishing their mission. So, for example, this on the right, this is the on the left, I'm sorry, is the well-formed infrastructure, because each robot standing on the circle, it won't block other robots to go into other locations, but this is not the well-formed infrastructure on the right. And basically our algorithm, it is very good in terms of this solution cost. So here you see these bars, our algorithm is on the green, and other bars, they are from this state-of-the-art. Red is ICBS, improved CBS, which was state-of-the-art in 2016, 2017, and it's actually the algorithm which returns you the optimal solutions, but only on 4 connected grids. So in case we're introducing this any angle moves, we're getting better solutions, like cost reduction is up to 20%, which is good. Basically, it means that Amazon can earn more money because their robots are doing their jobs faster. Yeah, and actually the success rate under the time limit is very good, because all those optimal planners, you see it on those red lines, these are the optimal planner. It's really time demanding to get optimal solution. So from practical point of view, maybe sometimes it's just not worth it. That's the runtime. That's the demo, just the animation. So you have this green, you have these blue circles, which are robots, and each has to navigate to its goal. When it comes to its goal location, it is shown in green. So those guys in green, they are occupying their goal locations. Yeah, and that's, yeah, everybody has safely reached the goal. Here are the paths, so you can see that these are not the zigzag paths, but that's how it is in robot operating system. That's the modeling software, where you can look at how your algorithm will be executed on the models of the robot, not on the real robots, but on the models of the robot. So again, you can see these are called turtle bots. They look pretty much like shaky. Yeah, that's our animation, and that's what's going on in simulated environment. We also have some enhancement. We added taking orientation into account, and we have evaluated this approach on the wheeled robot. We compared it with this reactive algorithm on the right, which is not planning the path, but just go straight to the goal and use some reactive collision avoidance. It's called ORCA. CA is for collision avoidance. So we are doing better, right? And that's the evaluation. I just wanted to say a few words. So you see that. So yeah, these 3 robots and those 2 robots on top, they have to switch, right? So these 3 have to go there, those 2 have to go downwards. Obviously, and there is a narrow passage. Obviously, if everybody just wants to go as fast as he can, they will collide into each other in this passage. So someone has to yield and stuff like this. And that's what our algorithm does. It just plans the path. So it just plans all the waypoints. It just plans how much to wait at those waypoints, and then those robots, they are not doing any, like local sensing and stuff like this. They are just following the path, right? The path that was produced by this, by the algorithm. So you see these guys on top, they have to yield, so they move away, and the duration, the duration of the wait action, how long they have to wait, it is computed by the planning algorithm, and they just execute it, and you see everybody reaches the goal safely. we also elaborated on this, like on deterministic rescheduling and start-save intervals. These are the techniques that enhance the effectiveness and efficiency of this prioritized approach, so we can get better success rates. I'm not sure whether I didn't have any time, but yeah, we're enhancing this prioritized approach thing. We make it work more nice. And now we're working with the authors of this CBS, with one of the authors of the CBS algorithm. We are trying to create the optimal solutions for this continuous time thing. So the paper is submitted to each guy, but the competition is really tough there, so I'm not sure what will be the output there. A few announcements for those who are interested. So we have this workshop on AI for unmanned vehicles, which will be in St. Petersburg in May. So you can follow this link and get some information. And for students who are watching it, there will be a summer school on artificial intelligence. I'm one of the organizers of the schools as member of Russian Association for Artificial Intelligence. So again, you can just follow it and apply for it. So yeah, thank you for your attention. If you have any questions, you can go with them now.
Thank you. Questions?
Are there competitions for trajectory planning? Like in data science, there are many competitions with some data science, and then there are test sets for which the labels are hidden. Does something similar exist?
I know that. So the problem, if you can look on these things from two points of view. So if we are talking about these mobile robots, it's obviously really hard to make everyone compete with real robots, right? Because we cannot provide everyone, every lab has its own robots, right? To solve this pathfinding thing. If we are talking about the simulation, I mean just the algorithms, yes, there is a competition which is called grid-based pathfinding competition, GPC. So these are just pathfinding on the grids. So there is some competitions in simulated environments for robots where you have basically solved this map thing, multi-agent thing. It's not that you have to do only the pathfinding. You have to do all this automated warehouse thing. So you have to, to assign tasks, but you obviously need to solve pathfinding as one of the components. So yeah, I mean, in case you have some of these algorithms, you probably can go for it.
Did I understand it correctly that when you talk about multiple agents, you assume that there is a so-called a central planning unit, which is
correct.
Who goes where?
Correct. Yeah.
So these kinds of algorithms, they're not really applicable for, say, driverless cars.
Well, in case all driverless cars can interchange the information, so it's not that we obviously need to have some central unit which knows everything. We assume that we can look at this that each agent knows everything about other agents. But yes, I mean, it's true in case you do not know something from one of the agents of your group, you're in trouble, you have to do something with this. So, but when we were elaborating on this, basically, you actually cannot do nothing. So in case you do not know nothing about this robot, you're not seeing him, you actually cannot predict that it will, like come in front of you. So basically, the thing that you can do this centralized planning first, and then when you're executing the plan, and then you see that there is another guy, you can do some reactive, this collision avoidance things just to repair this plan on while the plan is being executed. Or you can trigger replanning at this point of time, so you can ask this guy where you're going. It will say you, so I'm going to this point, this is my trajectory, and you can replan taking this trajectory into account. But yeah, I mean, like the answer is that you are correct. This is the centralized version of this multi-agent pathfinding thing.
Any other questions?
Questions in Russian? I can translate.
Well, if not, then thank you again.
Thank you.